Hi and Assalamualaikum. Today our group would like to present about the application of ceramics in telecommunication devices. This presentation is brought by ATHIRAH Sengkaning, NORASHIKIN binti Azmi, and Akmal Sajidah binti Muhammad Ray. Our presentation will consist of 4 components, which is for the first one is the introduction, second, the composition of the LTCC, third, the mechanism of the application, and fourth, the advantages of the LTCC. The telecommunication technology industry today requires high volume and low cost circuit fabrication, while at the same time demanding excellent electrical performance, reliability, circuit miniaturization, and surface mounting techniques. This information is brought by Barnwell and Miyake. The types of ceramics that we will focus today is the low temperature coal-fired ceramics, LTCC. It is the combination of dielectric ceramic layers with embedded electrodes made of high conductivity metals such as silver or copper. It is one of the most rapidly produced integral passive that provides a method for incorporating passive components such as capacitor, resistor, inductor, resonator, and filter into a multi-layer ceramic module by interconnecting layers of each part. LTCC technology provides a promising way to realize high-quality multi-chip modules which have huge market prospects. To develop the LTCC technology in the telecommunication device, these areas cannot be neglected, which are: the first one is the development of the material and the process. The second one is the component design and reliability. The electrical and thermomechanical demands for enhancing the manufacture and use of effective components are evident in the construction of a novel dielectric material for the LTCC device.
I am NORASHIKIN binti Azmi. I will explain about the composition of LTCC. This figure shows the two sample preparation procedure producing composition label as ZSBG MMT20 and ZSBR MMT20 respectively. The MMT20 comes from a commercial name of the dielectric ceramic powder of MgCaTiO3, the firing temperature of which has been decreased by using a mixture of zinc, silicon, and boron oxide. Index G in bracket denotes that the mixture has been prepared using glass, and R denotes the straight utilization of the raw material oxide. Following of the route for producing the mixture ZSBG MMT20, glass was first produced by baking the starting oxides and mixing for 1 hour in a polyethylene ball mill using a gate platinum crucible. The mats were quenched in water, pulverized in the ball mill for 12 hours, dried and screened through a 100 mesh sieve. The test mixtures were then prepared by weighing different amounts of glasses and MgCaTiO3 ceramic mixed in the ball mill for 2 hours together with polyvinyl alcohol as a binder, polyethylene glycol as a plasticizer, and distilled water. The composition was dried in a microwave oven and sieved. Axial pressure and firing were the used to form differentiate of compacts for various measurements. Later on, when the most suitable composition with competitive dielectric properties and a high density totally crystalline microstructure was found, a straightforward route without any glass preparation. Producing the final mixture of the SBR MMT20, the same mixing and sieving procedure was also used for pure MgCaTiO3. Now, shrinkage behavior of the ZSBG MMT20 and ZSBR MMT20 composition. Different amounts of the ZSBG glass were mixed and granulated with MMT20 dielectric, and the sinterability of this composition was measured using the dilatometer. First, this picture shows that 70 WT% of the ZSB glass was needed for good densification, which occurred in two stages. The first stage of sintering started at around 600 degrees Celsius and the second one at about 850 degrees Celsius. The SEM or EDS and XRD data for the materials in the S-mix and right condition, and after firing at 620, 875 and 900 degrees Celsius was studied, and the density and porosity of the samples were measured. In the second set of samples fired at 18 and 75 degrees Celsius for 80 minutes, no amorphous phases could be found, and the density of the sample was 3.1 milligram m to the power of -3 with porosity of 14%. In the third test series, after firing at 900 degrees Celsius for 80 minutes, the porosity of the sample was about 3.5% and the density is 3.5 milligram m to the power of -3.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal Sajidah binti Muhammad Reh with ID number SC10810. I in charge to explain the mechanism of LTCC for the title Application of Ceramics in Telecommunication Device. First of all, in this technology, several thin layers of low permittivity ceramic composites and conductor are combined and resulting multi-layer LTCC modules. Next, the LTCC enables a versatile mix of passive microwave components like microstrip, antennas, resonators, and capacitors, making possible a whole matrix of design that are not practical on regular alumina or any soft substrate. These integrated components are interconnected with 3D strip-line circuitry. Among the various components that could be realized in LTCC packages, that resonator and internal capacitors are important in terms of the latest technology. Next, there are two requirements. The first one is the internal capacitor are required to realize decoupling capacitor monolithically in LTCC packages. And the second one is resonators are needed for filter of quarter wavelength on the LTCC layer. The most important parameter for the LTCC technology is the low sintering temperature. Since the LTCC tapes can be sintered at low temperature, which is below 950 degrees Celsius, the embedded microwave component and transmission line can be fabricated using highly conductive and inexpensive metals. Metals such as silver, gold, or copper are low conductor loss and low electrical resistance at high frequencies. Several novel LTCCs with low dielectric loss and moderate and temperature compensated relative permittivity has been developed. This technology can be seen as very desirable. If low thermal expansion, high strength, and high thermal conductivity of the LTCCs and high frequency circuits require for high-speed data communication. That's all from me. Thank you for lending me your ears.
Let us move on the advantages of LTCC in the telecommunication devices. So what's the advantage of LTCC? LTCC technology possesses several advantages, making it suitable for mass-market telecommunication applications. The process itself enables high yield, reduced cost of devices with 3D microwave structures, and fast turnaround. This combination, together with the possibility of fabricating fine conductive line and spaces, small interconnect vias, and high dielectric layer counts, leading to high-density packaging. The general advantages of LTCC also includes the high-performance electronic packaging and substrate technology. It also ideally suited to radio frequency and microwave products. LTCC also have high temperature and harsh environment suitability. It has good electrical performance and good thermal properties. And lastly, it is a cost-effective for dense package due to parallel processing of layers. Now let us take a look of the advantages of LTCC has over other material. For the first one is the LTCC advantages over organic printed circuit board (PCB). LTCC has higher operating temperature up to 350 degrees Celsius. It has lower expansion coefficient and also higher integration density that embedded passive and higher layer count possible. It also has higher reliability that eliminates interconnections by integrating passive. It has smaller package size due to the integration. And lastly, superior high-frequency performance. Next is the LTCC advantages over high-temperature coal-fired ceramics, which is the HTCC. LTCC is a lower resistant metallization such as the gold, silver, tungsten. It also has higher number of layers, has lower tooling costs, shorter prototype cycles, and higher flexibility of post-pre-metal and dielectric options. And lastly, it has lower dielectric constant ceramic tapes available. So that's all from our group presentation. Thanks for watching.